Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today, we are going to discuss states of matter chapter, and in this chapter, already we have completed up to Graham's law of diffusion. Next topic in this chapter is kinetic theory of gases. So, we are going to discuss it now. Please listen carefully. So, kinetic theory of gases. Now, we are going to start. Yes. So, what is kinetic theory of gases? Now, we are going to discuss. So, please listen carefully. This is the next topic in this states of matter chapter. The kinetic theory of gases was proposed by Bernoulli in 1738, developed by Clausius, Maxwell, and Boltzmann. Postulates of the following. So, what are the kinetic theory of gases postulates? Let's listen now. First point: gaseous molecules are considered to be point masses. So, these gaseous molecules are considered to be point masses. They are considered to be point masses, and the volume of a molecule of a gas, very important point. The volume of a molecule of a gas is negligible as compared to the total volume of the gas. So the volume of the molecule of a gas is negligible compared to the total volume of the gas. So this is called second postulate. Next, we are going to the next postulate. So first postulate, gaseous molecules are considered to be point masses, and the volume of a molecule of a gas is negligible when compared to the total volume of the gas. Next, third postulate. Gaseous molecules do not have appreciable attraction. Hence, gases can be easily compressed and do not have fixed shape and volume. Third point, gaseous molecules do not have appreciable attraction. So there is no attraction between the gas molecules. Hence, gases can be easily compressed and have fixed shape and volume, do not have fixed shape and volume. As we know, solids and liquids have fixed shape and volume, but gases do not have because they do not have appreciable attraction. What is that attraction means? The gas molecules, suppose you consider a gas, hydrogen gas, it's consisting of gas molecules, hydrogen molecules. So these molecules do not have any attraction. So as gas molecules do not have appreciable attraction, hence gases can be easily compressed by applying pressure. So by applying pressure, we can compress gas. By applying pressure, we can compress gas. So by applying pressure, we can easily compress a gas. That's why gases are highly compressible. Gases are highly compressible. And gas molecules collide with each other, but their collisions are perfectly elastic. What do you mean by elastic? There is no loss of energy or gain of energy. So there is no net loss of energy. That's why it is called perfectly elastic. This point is important. Gas molecules collide with each other, but their collisions are perfectly elastic. And they collide with the walls of the container and also they collide with each other. So when they collide with the walls of the container and collide with each other, they develop pressure. So that's why gases exerts pressure. So gas molecules collide with each other, but their collisions are perfectly elastic. Their collisions are perfectly elastic. There is no net loss of energy. Suppose consider two molecules A and B with mass m. Their speeds are first gas molecule with velocity A, second gas molecule with velocity B. So VA and VB respectively. After collision, let the new speeds will be VA and VB respectively. So VA dash and VB dash. So VA dash and VB double dash respectively. As the collisions are perfectly elastic, we can say total energy before collision is equal to total energy after collision is equal to total energy after collision. Let us see. So kinetic energy they have. So half into mva square. So because the gas molecules move randomly in all the directions, so they move with kinetic energy. What is that energy is called? Kinetic energy. What is the formula of kinetic energy? Half mv square. Half mv square is at formula for finding kinetic energy. So that is half into mass of the gas molecule into velocity of the gas molecule square. So the before collision, what are the molecule speed? That is half mva square plus half mvb square is equal to half mv dash a square plus half mv dash b square. By this taking m, because the mass of molecule is constant, so taking m common, m and m gets cancelled on the both sides. Now we have only va square plus vb square is equal to va dash square plus vb dash square. By this what we can understand, the collisions of the gas molecules are perfectly elastic. The collisions of the gas molecules are perfectly elastic. Next important point, the average kinetic energy of a molecule is directly proportional to its temperature. The average kinetic energy of a molecule is directly proportional to its temperature. This point is very, very important. Based on this point, they'll ask examination, competitive exams one question. So this question is very important. The average kinetic energy of a gas molecule is directly proportional to its temperature only. Means if the temperature increases, the average kinetic energy of the gas molecule also increases. And if the temperature decreases, the average kinetic energy of a gas molecule also decreases. So this is very, very important postulate. So next continuation. There is no effect of gravity on the molecular motion. There is no effect of gravity on the molecular motion of the gas. So the gas molecules move randomly. If they have effect of gravity, they should fall. But it is not happening. That's why we can say easily there is no effect of gravity on the molecular motion. That's why even if you release a gas balloon also, it will fly in the air. It will not come down easily. So that's why we can say there is no effect of gravity on the molecular motion. The pressure exerted by the gas molecules is due to the collisions with the walls of the container. As I told you, the pressure exerted by the gas molecules is due to the collisions with the walls of the container. So these are the important postulates of kinetic theory of gases. So from these postulates, we have got kinetic gas equation also. So how do gases exert pressure? They exert the pressure due to the collisions with the walls of the container. As the molecules move randomly in all the directions, they collide with the walls of the container also. By this only gases exerts pressure. I hope it is clear. So these are all the postulates of kinetic theory of gases. Next continuation. Now, kinetic energy and molecular speeds. Very, very important, kinetic energy and molecular speeds. Now by this, we have got a new gas equation that is called kinetic gas equation. This derivation they will discuss with you in the board exam, so in the board syllabus. So for competitive exam or entrance exams, we do not have any derivation of this. PV is equal to 1 by 3 mc square. So what is the kinetic gas equation? Kinetic gas equation is equal to PV, that is pressure into volume, is equal to 1 by 3 Mn, where M is called mass of the gas molecule, N is called number of moles, and C is called velocity. C is called what? Velocity. So by this we can say PV is equal to 1 by 3 Mnc square is the new kinetic gas equation. PV is equal to 1 by 3 Mnc square, where M is equal to mass of gas molecule, mass of gas molecule, N is equal to number of moles, and c is equal to speed of gas molecules or velocity of gas molecules. So velocity of gas molecules. It is not with respect to light, speed of light. So velocity of gas molecules. So this is called kinetic gas equation, where P is equal to pressure, V is called volume. So PV is equal to 1 by 3 mc square is known as the kinetic gas equation. So please remember this equation. It's very, very important. So PV is equal to 1 by 3 mc square. For 1 mole of a gas, N is equal to Avogadro number. So sodium, for example, so N into M is equal to mass into sodium atom. So we can say, and M is called molecular mass. So M is equal to, we can say PV is equal to 1 by 3 mc square for 1 mole of a gas. Simply we can say PV is equal to 1 by 3 mc square, where M is called molecular weight of the gas. Very, very important. Molecular weight here. M is called what? Molecular weight, because Na is equal to 6.023 10 to the power of 23 into M is called mass of each gas molecule. So we can say M is equal to PV is equal to 1 by 3 mc square for 1 mole of a gas. Kinetic energy and temperature. Now, what is the dependence between kinetic energy and temperature? Suppose 1 mole of a gas is under consideration. The number of molecules involved will be N of A. Then according to the kinetic gas equation is equal to 1 by 3 mc square. We PV is equal to 1 by 3 mc square for 1 mole of a gas. So PV is equal to RT. Since PV is equal to RT, because for 1 mole of a gas, from ideal gas equation, we know PV is equal to nRT. Then for 1 mole of a gas, PV is equal to how much? Because N is equal to 1 mole. So for 1 mole of a gas, we can say PV is equal to RT. PV is equal to what? RT. Where R is called universal gas constant, T is called temperature. Now we are going to write the relation between kinetic energy and temperature. So by this you can say PV is equal to RT, RT is equal to 1 by 3 mc square, where m is called molecular mass of the gas. So by this you can say RT is equal to 2 by 3, multiplying and dividing by 2 by 3. So we can say 2 by 3 into half mc square, 2 by 3 into half mc square. You can see the step because you can see 1 by 3 mc square is equal to multiplying and dividing by 2. So we can say 2 by 3 into 1 by 2. This were 2 and 2. So this 2 and 2 we are having multiplying and dividing. By this what you can say, we can write kinetic energy because half mc square is equal to kinetic energy. So by this we can say RT is equal to PV is equal to 2 by 3 kinetic energy. So by this, what is the relation between kinetic energy and pressure and volume? So PV is equal to 2 by 3 KE, or RT is equal to 2 by 3 KE. Please listen carefully. This is here from this step. Since we know PV is equal to 1 by 3 mc square for 1 mole of a gas. So by this we can say RT is equal to 1 by 3 mc square, implies RT is equal to multiplying and dividing by 2. Here you can see multiplying and dividing by 2. If you do multiplying by dividing by 2, why you are doing it? Because we want to relate the gas equation with kinetic energy. So that's why we have done multiplying and dividing by 2. Here itself I'll write multiplying and dividing by 2. Multiplying and dividing by 2. Dividing by 2. So if you multiply with 2, 2 by 3 and divide by 2, 1 by 2. So 2 by 2 gets cancelled. So that's why we can write multiplying and dividing by 2. We got 2 by 3 into 1 by 2 mc square. That is 2 by 3. 1 by 2 mc square is called kinetic energy. So we can say 2 by 3 into 1 by 2 kinetic energy. So this we can say 2 and 2 gets cancelled. So that's why we can say 2 by 3 kinetic energy. So this is a relation between pressure and volume with respect to kinetic energy. So this is a relation for the kinetic gas equation with respect to kinetic energy. So what is the kinetic gas equation with respect to kinetic energy? PV is equal to 2 by 3 kinetic energy. PV is equal to 2 by 3 kinetic energy. I hope it is clear. So this is called kinetic energy with respect to gaseous state. Next continuation. So K is equal to 3 by 2 RT per mole, or ET is equal to energy is equal to 3 by 2 RT. So 2 by 3 RT, 3 by 2 RT. But PV is equal to RT is equal to 2 by 3, where we can say here, you can just see here, where ET is called translational kinetic energy for 1 mole of a gas. What is ET? Translational kinetic energy for 1 mole of a gas. Now kinetic energy is equal to 3 by 2 RT. We got, this is one more equation. So kinetic energy is equal to 3 by 2 RT, because same, because how we got this equation? Since kinetic RT is equal to 2 by 3 kinetic energy. By this we can say K is equal to, so 3 by 2 RT. 3 by 2 RT. So this is called kinetic energy is equal to 3 by 2 RT per mole. And this kinetic energy, we also call it as translational kinetic energy. What we will call it as translational kinetic energy for 1 mole of a gas. So by this we can say kinetic energy is equal to 3 by 2 into R by N naught. This is very, very important. Please note down, this is R is called universal gas constant, N naught is called Avogadro number. So 3 by 2 N naught into T. 3 by 2 R by N naught into T per molecule. For if this is for 1 mole of a gas, and for per molecule, if you take R by N naught, where N naught is called number of molecules per molecule. So by this you can say K is equal to 3 by 2 KT, where K is called R by N naught is called R by N naught is called K, where K is called Boltzmann constant. Boltzmann constant. K is called what? Boltzmann constant. So this is called Boltzmann constant. So by this we can say Ke is equal to 3 by kinetic energy is equal to 3 by 2 R by N naught into T. Since R by N naught is equal to K, that is called Boltzmann constant, we can say kinetic energy per molecule is equal to 3 by 2 KT. By this, we can say kinetic energy is proportional to temperature also. So kinetic energy is proportional to temperature as well as number of moles of the gas. Since kinetic energy is proportional to two things, average kinetic energy here, important point you see here, please. So average kinetic energy is proportional to only temperature. Average kinetic energy, these 2 points are very important. Please note down in your classwork. Average kinetic energy is proportional to absolute temperature only, whereas kinetic energy of the gas molecules is proportional to kinetic energy, that is Ke is proportional to N, as well as it is also proportional, kinetic energy is also proportional to T, is also proportional to. So it is depending upon, kinetic energy is depending upon number of moles of the gas as well as absolute temperature. Very, very important. Kinetic energy is proportional to number of moles as well as temperature, absolute temperature of the gas. Whereas average kinetic energy is depending only on absolute temperature. It is independent of number of moles. So please note down this point in your classwork, because based on these 2 points, they'll give frame a question for competitive exams. How they'll frame a question for competitive exams, I'll explain you later. So after finishing this topic. So average kinetic energy is proportional to absolute temperature, whereas kinetic energy is proportional to number of moles as well as absolute temperature. That is the only difference. Hence, translational kinetic energy of an ideal gas is directly proportional to absolute temperature. So only translation kinetic energy is proportional to absolute temperature. So now important concept in this. So I hope it is clear, all these points. Next, Boltzmann constant K is equal to gas constant per molecule. So R by N naught is called, as I told you, R by N naught is called Boltzmann constant. So N naught is equal to number of molecules. It is equal to Avogadro number of molecules. And R value, that is 8.314 joules per Kelvin per mole. By substituting these two, we can say R is equal to Boltzmann constant value is equal to 1.38 in 10 to the power of minus 23. What is the value of Boltzmann constant? So that is Boltzmann constant K is equal to 1.38 in 10 to the power of minus 23 joules per Kelvin per molecule. Joules per Kelvin per molecule. So very important difference is Boltzmann constant is for per molecule of a gas. Per molecule. Gas constant per molecule. Gas constant per molecule is also called as Boltzmann constant. So kinetic energy is equal to 3 by 2 RT, 3 by 2 nRT. For n moles of a gas, what is the formula for kinetic energy? Kinetic energy is equal to 3 by 2 nRT for n mole of a gas. Very important, very, very important formula. For n moles of a gas, for 1 mole of a gas, it is 3 by 2 RT. For n moles of a gas, kinetic energy is equal to 3 by 2 nRT. That's why I told you kinetic energy is depending on number of moles as well as absolute temperature, whereas average kinetic energy is depending only on absolute temperature. These points are clear. So all these points are very, very important. From these points also, you'll get definitely one competitive exam question. So entrance exam, they'll give based on these points only. How they'll frame a question also, I'll explain you after finishing this topic. I hope. Next continuation. Next, we have, what is the new topic we have? Maxwell-Boltzmann distribution of molecular speeds. Since we have completed kinetic theory of postulates, next topic in this chapter is Maxwell-Boltzmann distribution of molecular speeds. At a particular temperature, different molecules of a gas possess different speeds. At a particular temperature, different molecules of a gas possess different speeds. Since the kinetic energy of the gas molecules is proportional to temperature, absolute temperature. So as we increase the temperature, the gas molecule speed also increases. Further, as a result of continuous collisions among the molecules and against the walls of the container, as a result of continuous collisions among the molecules and against the walls of the container, their speeds keep on changing. However, Maxwell and Boltzmann showed that as a result of collisions, though some molecules are speeded up, some others are slowed down, and thus the fraction of molecules possessing particular speeds remain constant at constant temperature. So this point is very important. Please note down. The fraction of molecules possessing particular speeds remain constant at constant temperature. So if this fraction of molecules possessing particular speeds are plotted against their corresponding speeds at a particular temperature, so fraction of molecules delta n by n and molecular speeds at a particular temperature, that is in figure 3.7 we have given, it is obtained. A curve is obtained. What is obtained? A curve as shown in the figure is obtained. This distribution of speeds is known as Maxwell-Boltzmann distribution. Sorry. From this curve, the following observations are the following are observed. What is the first point we observed? The fraction of molecules with too low or too high speeds are very small. So we have only a few molecules are undergoing too low speed or too high speeds. That's why you can say the fraction of molecules with too low or too high speeds are very, very small, few. Actually, we can not say small, we'll say few. Very few molecules possess either too low speed or too high speed in a gas. The peak of the curve corresponds to a speed possessed by the maximum. This is called the peak of the curve. This peak of the curve corresponds to a speed possessed by the maximum fraction or the maximum number of molecules. So maximum number of molecules will have most probable speed. This speed is known as most probable speed and it is represented by C star. C star is called most probable speed. Most probable speed. So MPS we can say it is called. So C star. So the peak of the curve corresponds to a speed possessed by maximum fraction or maximum number of molecules. As I told you before, first point, what they observed after the plotting of the graph between fraction of molecules and their respective molecular speeds, very few molecules only will have either low velocity or low speed or high speeds. And maximum, the peak of the curve corresponds to speed possessed by maximum fraction of molecules or maximum number of molecules. This speed is known as most probable speed and is represented by C star. It is represented by what? It is represented by C star. Continuation. So the peak, the important concept you can see here, the peak whole curve shifts forward, which shows that the most probable velocity increases at different temperatures. You can see here, this is about three different temperatures, T3, T2, and T1. The peak whole curve shifts downwards, which shows that the fraction of molecules or number of molecules possessing most probable velocity decreases. So as it is occupying peak, afterwards what happens, it start decreasing. It means that what, the peak shifts downwards, which shows that the fraction of molecules or number of molecules possessing most probable velocity decreases. The curve is flattened, becomes broader in the middle, which shows that more molecules have speeds near to the most probable speeds. So this curve broadening, so broadening of this curve shows that they have average speeds. These fractional molecules are called what? They have average speeds and their speeds are near to most probable speeds. The fraction of molecules with higher speeds increases and the fraction of molecules with lower speed decreases. So by this we can say all the gas molecules will move with three types of velocities. What are those? We'll discuss now. It is, however, important that to note that the total area under each of the curves remains the same as the sum of the fractions of the molecules remains the same at any temperature. This point is important. Just note it down. What is this point represents? It is, however, you can say important to note that the total area under each of the curves, total area under each of the curves, you can see these dotted lines, remains the same as the sum of the fraction of molecules. Sum of the fraction of molecules remains the same at any temperature. So now types of molecular speeds we have only, as I told you, three types of molecular speeds. One is root mean square speed, another is average speed, third one is most probable speed. So they noticed after finding this graph, they have come to conclusion that gas molecules move randomly in three types of molecular speeds. How many types? Three types. What are those three types? We have first we have root mean square velocity, that is also called as RMS velocity. RMS velocity. Next we have average speed. RMS velocity denoted by the letter C. Next we have average speed. What we have? Average speed. Average speed. Next we have average speed. It is denoted by letter CRMS. No, this is not CRMS. This is C average. We can say C average. Next we have most probable speed. Most probable speed, that is also called as C star. So we have three types of speeds a gas molecule will have possibly. First is root mean square velocity. second is average velocity, third is most probable velocity or most probable speed. So first what we'll see, root mean square speed, the total kinetic energy of n molecules of a gas. The total kinetic energy of n molecules of a gas is the sum of the kinetic energy of all the molecules, individual molecules. The sum of kinetic energy of its individual molecules. So let's say it has n molecules. So we can say half mc1 square, that is speed of first molecule, half mc2 square, that is speed of second molecule, half mc3 square, that is speed of third molecule, and so on up to half mcn square. Let C be the velocity possessed by each molecule of the molecule possessed by each of the molecules. Let C be the velocities. We can say total kinetic energy is equal to n into half mc square. That is n into half into mc square is equal to mc1 square plus mc and so on. That is sum of the speed c1 square plus c2 square plus c3 square. Next, by this we can say c square rms is equal to c1 square plus c2. Since m is constant, we can write c1 square plus c2 square plus c3 square and so on up to cn square by n. By this we can say c rms is equal to root of, because c square, this is c square. So for this root of this one will come. So a much a much precise representation is c rms is equal to root of n1c square plus n2c square, where n is called number of moles. So by this you can say, since n1 is equal to n is equal to n1 plus n2 plus n3, we can say CRMS is equal to root of n1c square plus n2c square plus n3c c3q n3 into c3 square plus so on up divided by n. Next we have average speed. It is defined as the arithmetic mean of various speeds of the molecules. It is also equal to root of 8 RT by pi m, where R is called gas constant, T is called temperature, pi is called, the constant, and it is m is called molecular weight. So by this you can say relation between average speed and RMS speed is 0.9213 into C into RMS. So RMS is equal to 1.08 into C average. So this is a relation between C average and C RMS, and this is, we can say, it is nothing but root mean square velocity. And we have average speed, which is also written as 8, the arithmetic mean of various speeds of the molecules. The arithmetic mean of various speeds of the molecules is called average speed. It is root of 8 RT by pi m. I hope it is clear. So next continuation. So a gas molecule possesses how many types of speeds? Three types of speeds. What are those? Root mean square velocity, average velocity, and one more is what? Most probable velocity. Most probable velocity. Next continuation. So third type of speed is called what? Most probable velocity. The speed possessed by maximum number of molecules of a gas at a given temperature is called most probable speed or most probable velocity. It is given, it is done by the formula C is equal to C MPS is equal to root of 2 RT by M, root of 2 RT by M, which is equal to root 2 by 3 into RMS, that is 0.816 into C RMS into C. So this is called most probable velocity. The relation between all the three is very important. You can just notice it. C most probable versus C average versus C RMS. The relation is root 2 root of 8 by pi root 3, that is equal to 1 is to 1.128 is to 1.224. Because since we already know, since root mean square velocity C RMS is equal to root of 2 RT by pi, root of 2 RT by M, root of 2 RT by M, where M is called. Again, I'm writing here as it is not clear. So C RMS is equal to root of 2 RT by M, where M is called molecular weight. And C average is equal to root of 8 RT by pi into molecular weight. And C most probable velocity is equal to root of, sorry, this is 3 RT by M, and this is 8 RT by pi M. So root 3 RT by M, and this is root 2 RT by M. So what is the relation between all the three? 1 is to 1.80, 1.128 is to 1.224. So further, since kinetic energy is equal to half mc square, so K is equal to C square and K is proportional to T. So C square is proportional to T, or C is equal to root T. Hence, the molecular velocity of any gas is proportional to the square root of the absolute temperature. We can say the molecular velocity of any gas is proportional to square root of the absolute temperature. Therefore, the molecular motion in a thermal is a thermal motion of the molecules. At absolute zero, it is found that the kinetic energy is equal to zero. Since already we know what is absolute zero means where the molecular motion ceases. So, as the molecular motion ceases at absolute temperature, we can say kinetic energy also zero. So in other words, the thermal motion ceases completely at absolute zero. So while calculating U, one should keep in mind the following things. That is CJ's unit is centimeters per second, dynes per centimeter square, and mass, that is what is the unit of U? U is called velocity, P is called pressure, V is called volume, and M is called molar mass, and R is called gas constant, D is called density. So all these things is not that much important. So molecular speeds of a gas is curiosity question. Now you see this curiosity question. Molecular speeds of a gas molecules are analogous to those of rifle bullets. Why this order of a gas not detected so fast? Although the molecules of a gas travel at high speeds, they do not travel in straight lines in one direction only like bullets. As they travel, they collide with the molecules of the gases that are present in the air. As a result, they become deflected. Hence, they follow a zigzag path. That is, the net distance traveled by in a particular direction is quite small in a given time. Hence, the order is not detected so fast. So far, we have not detected. That is an example question based on molecular speeds of gas molecules are analogous to those of rifle bullets. Bullets will go in one direction only, but whereas the gas molecule will not go in one direction. It is not going in one direction. They collide with each other. So the total energy of a molecule is divided exactly among the various. Now, what is this equipartition of energy? Next concept in this equipartition of energy. The total energy of a gas molecule is divided equally among the various degrees of freedom of a molecule. So the distribution of kinetic energy along the axis x, y, and z is called Ek is equal to Ekx, Eky, and Ekz. That is x-axis, y-axis, and z-axis. That is the energy. So by this we can say 1 by 3 into 3 by 2 kT. By this you can say 1 by 2 kT, where k is called Boltzmann constant, R by N naught or R by Na. So this is called equipartition of energy. It means the energy will be equally distributed among all the molecules. What you can say about this? The energy will be equally distributed among all the molecules. Next, this shows that the component of kinetic molecular theory, kinetic energy, and that the kinetic energy for each degree is 1 by 2 kT per molecule or 1 by 2 RT per molecule. So by this, what we can say, the vibrational motion of a gas molecule is associated with the energy. Two types of energy. What are those? One is potential energy, and another is kinetic energy. Since the gas molecule will have two types of energy, potential energy as well as kinetic energy, thus total vibration energy is equal to potential energy plus kinetic energy. By this, you can say 2 into 1 by 2 kT, that is 2 into 1 by 2 RT per mole. That's why we can say 2 by 3 and 1 by 2. 1 by 2 and 1 by 2. We got 2 into 1 by 2 kT per mole. So, now example. Under 3 atmospheric pressure, 12.5 liters of a certain gas has a weight 15 grams. You can see here, this is the question based on molecular speeds. Under 3 atmospheres, pressure is given. 12.5 liters of a certain gas has a weight of 15 grams. What is the average speed of the gaseous molecules? So this is the model number 1. So based on this, they'll ask average speed of the gas molecule. So we know already average speed, that is U average is equal to root of 8 RT by pi m. So since RT is equal to PV, we can say PV RT by M is equal to, so we can say since using the equation PV is equal to W by M RT, because we know since gas molecules PV is equal to nRT, but we can say PV is equal to W by M, where weight of gas molecule by molecular mass of gas molecule into R into T. So W by R into T. And they have not mentioned a gas having a weight of 15 grams. So we can say they're asking average speed of gas molecules. So this is equation 1, that is root of pi RT by 8 RT by pi m. So given P is equal to 3 atmospheres, V is equal to 12.5 liters, volume is equal to, W, weight is equal to 15 grams. Using the gasification, we can say PV is equal to W by MRT. So we get 3 into 1.12.5, that is 12, 3 into 12.5 is equal to 15 by M into 0.0821 into T. T is constant, so T by M is equal to 30.45. By this, you can say from the equations 1 and 2, we get U average is equal to 8.03 10 to the power 4 centimeters per second. Even straight away, also, you can apply the formula. U average is equal to root of 8 into R, that is 0. Since atmosphere is given, we have to say R value is equal to 0.081. Very important point to be noted. Since pressure is given in atmospheres and volume is given in liters, so we have to take R value 0.0821 and T value temperature as it is. So from the equations 1 and 2, we got U average is equal to 8.03 10 to the power 4 centimeters per second. Find the temperature at which carbon dioxide has the same RMS velocity as that of oxygen gas. They have compared this. So for oxygen, URMS is equal to root of 3 RT by M. Since we know the formula, URMS is equal to root of 3 RT by M. So root of 3 into R into 27, uh, 27 and by 32. So R into T by 32, that is 27 by 32. For carbon dioxide, because 27 by 32, for oxygen molecular weight is 32. And for carbon dioxide, URM is equal to root of 3RT by M, that is 3 into R into T by 44. So by this, you can say 3R by 273 by 32, because 273, as both are same, we can say 3RT by 3 is equal to, at what temperature asking, so seems only temperature we have to take. Find the temperature at which carbon dioxide has the same RMS velocity as that of oxygen. So we have to assume that this is 273 kelvins. 273 kelvins. So let us take oxygen is 273. Now carbon dioxide same temperature, we have to take 375.38 kelvin. So as both are same, therefore we can say, at what temperature the RMS velocity of carbon dioxide will be as that of oxygen, it is equal to 375.38 kelvins or 102.3838 degrees C. Next question. Calculate the total energy and average kinetic energy of 32 grams of methane molecules at 27 degrees C, and calculate the root mean square speed, average speed, and most probable speed of the methane molecules at 27 degrees C. So they are given two questions. So question one, number one, calculate the total energy and average kinetic energy of 32 grams of methane molecules at 27 degrees C. So we know methane molecule, so 32 grams of methane molecule at 27 degrees C, and calculate the root mean square. This question is very important, so listen carefully. So since already we know total kinetic energy is equal to 3 by 2 nRT, where n is called number of moles, and we know methane molecule number given weight is 32, and more number of methane formula is CH4, so atomic weight is 16. 16, because 12 plus 4, it is equal to 16. So 3 by 2 into 32 by 16 into 8.314 into temperature is given 27 degrees C. So it is 273. Temperature is equal to 273 plus 27. So we can say it is 300 kelvins. 300 kelvins. So after multiplying that, you'll get the answer. So that is equal to 74,282.6 joules. Now average kinetic energy is equal to 3 by 2 kT, where K is called Boltzmann constant. So that is equal to 3 by 2 into 8.314, that is R by N naught, that is 6.02 10 to the power of 23 into 300 Kelvin. So it is equal to 6.21 10 to the power of minus 21 joules per molecule. So instead of taking this 8.314 10 to the power 6 by 6.02 10 to the power of 23, we can write 1.38 in 10 to the power of minus 23 also, because it's the value of R, is the value of K value. K value is equal to 1.38 in 10 to the power of minus 23. So by substituting this, you got this is the value of average kinetic energy. So this is called average kinetic energy, that is 374.13 joules per molecule. 3 by 2 into 0.314 joules per molecule, Kelvin per molecule, so into 300. So you got next we have root mean square velocity. Root mean square velocity, we can say it as RMS velocity root of 3RT by M. So using CGS units, R is equal to 8.314 10 to the power 7x, T is equal to 300 kelvins. So molecular mass of methane is 16 grams per mole. So we got RMS velocity is equal to 683.9 meters per second. This is the this is the value we got. Using SI units, we got 683.9 meters per second. CGS units you can get like this in 10 to the power 4, or you can say 683.9 meters per second. Depending on the options in the examination, we can use either meters per second or centimeters per second. If they are given centimeters per second, R is equal to 8.314 into 10 to the power of 7x per Kelvin per mole. Only we have to change R value. Remaining all they are constants, because temperature we know that is they'll give at 27 degrees C means 300 kelvins, and molecular mass of this methane is 16, so we have kept it 16. So 16 10 to the power of minus 3, because this is in kilograms. So for meters per second, we have to take into 10 to the power of minus 3. So next, similarly, calculate the average speed and most probable speed by using equations. Root of CA is equal to C bar is equal to root of 8 RT by pi m, that is C average, and C star is equal to root of 2 RT by m, that is most probable speed. So, or you can take C bar is equal, that is C average is equal to 0.921 into C. Since we got already C, so 0.921 into 683.9. So you'll get this. And even C star is equal to 0.816 into C, that is 0.816 into 683.9. Because the relation between C average and C is 0.921 into C, whereas C star and C is 0.816 into C. What is C? C is called, C is called what? C is called RMS velocity, and C star is called most probable velocity, and C bar is called average velocity. So relation between C bar and C is it is equal to 0.921 into C, whereas relation between C star and C is it is equal to 0.816 into C. So I hope, so this is the answer we got with respect to meters per second. Next we have next concept in this chapter, that is called collision diameter. What is collision diameter? The kinetic theory of gases considers molecules as point masses. When two such molecules approach each other, these two masses approach each other, a point is reached at which the mutual repulsion between the molecules becomes so strong that it causes reversal of the direction of their motions. Though reversal of the direction of their motions, the distance between the centers of the two molecules is the centers of the two molecules at the point of the closest approach is called collision's diameter. So simple definition, the distance between the centers of the two molecules at the point of their closest approach is called collision diameter. Now what is collision number? The number of collisions with which a single molecule collides per unit time is called it is given by root of pi c square, that is pi into sigma square. So C average, where C average is equal to average velocity, P is equal to number density. That is the number of molecules per unit volume of gas is equal to, this is called collision frequency. So the total number of molecules that collide per unit volume of the gas is given by the equation root of 2 pi sigma square into C average into P square, that is root density, number density square. So as collisions involves two molecules, the number of collisions of like molecules occurring per unit time per unit volume of the gas is given by the equation Z is equal to 1 by O2, this much. So this is also known as collision frequency. What is the formula for finding collision frequency? Z is equal to 1 by O2 pi sigma square C average P square. P is called, that is rho square, that is called rho square. Rho is called number density square. This is also known as collision frequency. Also the number of collisions of the molecules of the type 1 with those of type 2 would be called as Z12 1 by O2 rho 1, rho 2, because two different molecules. Same molecules means you can write these two different molecules, we have to use this formula. Moreover, P is equal to KT, density is equal to P by KT, we can say 1 by 2 to P square by KT square. So this is called collision diameter and collision number. These are of not next concept. So the frequency is proportional to P square, and the frequency of the collision is also proportional to T power 3 by 2. It should be noted that Z1 is expressed in second inverse, that is frequency, because we know the units of frequency is expressed in second inverse. And mean free path is the mean distance traveled by a gas molecule between two consecutive collisions, and lambda is equal to average distance traveled per second by number of collisions by a molecule per second. So lambda is equal to C average by Z1, and we'll got this. So lambda is proportional to 1 by P. At constant temperature, lambda is proportional to T at constant pressure. So lambda is proportional to 1 by P at constant temperature and lambda is proportional to T at constant pressure. So this is the end of kinetic theory of gases. Now, before going to this behavior of real gases, deviations from ideal gas behavior, now we will start now problems related to kinetic energy. So that concept we'll discuss now. So in the coming session, so I'll take a separate slide and I'll do it. I hope it is clear. So we will discuss now problems based on kinetic energy, that is kinetic theory of gases. Problems based on that is competitive questions, because we have not discussed many questions, so it's important to discuss all those questions. After that, we'll discuss behavior of real gases and deviations from ideal gas behavior. So before that, I'll write all the important formulas in the new slide so that it is easy to understand, and then we'll discuss numericals for competitive exams or entrance exams. So I'm closing this session. So next session we'll do questions based on kinetic energy. Thank you all.